Hello, in this video tutorial I'm going to do a question from a recent OCR A further stats paper question on Wilcoxon Rank Sum test and the normal approximation thereof. You're given the formulae in the formula book for this test, but I really do think it is important to actually kind of have a concept of what we're actually doing with the Wilcoxon Rank Sum test. You can't just rely on the procedural way of doing it without actually having some concept of how it works. The particular question, because it involves a normal distribution and doesn't involve these critical values, is probably not the best example to introduce the Wilcoxon Rank Sum test. There are other videos that I've done which do that. But nevertheless, I think it probably ought to actually introduce the simple idea of how we do a Wilcoxon Rank Sum test for smaller numbers rather than a normal approximation first. So let's look at this question first, just for a moment before doing it. It's actually to do with two different journey times to school via two different routes. One of them has a sample of 17 journey times, and the other one has a sample of 12 journey times. Now notice in this question, which is why I say it's probably not the best example to introduce this as a concept, you are not actually given the raw data itself, simply how they rank compared to each other. So I think what I'll do is I will actually just make up some other numbers. Let's say just have the same context. Suppose we had route A, and there was actually a sample of, I don't know, sample of 4 on route A. Let's say the journey times are 17, 21, 24 and 25. And on route B, the numbers are 11, 12, 13, 14 and 18, say. Right, so what we do to actually rank these is to get this ranking number, this RM as described in the formula book, is to rank them from smallest to largest or vice versa. It's actually arbitrary, irrespective of which of these two groups they go in. So for example, the smallest is 11, the next smallest is 12, the next smallest is 13, next smallest is 14, so that's 4, but the next smallest there is 17 from the other group, and then 6 on 18, 7, 8, 9. And what we're told is that RM is the sum of the ranks of sample size M, where M is the smaller number, or arbitrarily either one, if there's the same number in each group. Okay, so what we do here is we'll look for the M is obviously the 4 here, and we can add these numbers together to work out our value for RM. So we've got 5 plus 7 plus 8 plus 9. That comes to 29. Now these are actually almost as big as they can be. If you think about it, the largest possible kind of score here for 4 of them would be 6 plus 7 plus 8 plus 9. So the largest possible is equal to 30, and the smallest possible is equal to 1 plus 2 plus 3 plus 4, which is actually equal to 10. So the distribution of RM would be a discrete distribution with the smallest possible being 10. There's only one way of doing that, so it's less probable. Then we've got 11, 12, and so on. I probably haven't got enough room to put them all on, but the mean of this would be 20, and let's see, that's there, 10, 11, 12, and the largest possible is 30. And what we're doing here is actually deciding whether these two numbers here, 29, is significantly too big or whatever as to actually assume that there must be a difference between the two sets. So that's what would happen if there were equal probability, that equal chance, equal times between root A and root B. 29 and 30 would randomly occur as actual scores for RM fairly infrequently, compared to 20, which would be in the middle of this distribution. However, the way it works for smaller values is that they do a kind of adjustment. So instead of actually testing these bigger numbers, they kind of get swapped by these numbers. And that's what this is all about, this calculation that we work out. So, or we do m plus n plus 1 minus Rm. In this case would be 4 times by 4 plus 5 plus 1 minus 29. So it's 40 minus 29, which is 11. Okay, so that's what this thing does, because then we're going to test the critical values. In this case, 11, well, depending on the test, it would actually not be possible to test it with this one, because 10% on a one tail doesn't even come in the values, critical values here. But 11, for example, we would be rejecting H0, because we would be looking at 4 or 5 if it were a two-tailed test at 5%. We would be rejecting it if it were a two-tailed test at 10% or a one-tailed at 5%. But we wouldn't be rejecting it if it were a 1% test, because that would be a value of 10, and the only way we can get 10, in order for it to be significant with this small sample size at a 1% level, we would literally need no overlap between the two groups, and all the smaller ones are on one set, and all the smaller ones are on all the larger ones are on the other set, and no overlap was what we'd need to have a significant rejection of H0 at that level, and which is actually incidentally why you see some dashes in the tables. So basically, there at a 1% level, it's not possible to actually have a significant outcome to reject all at H0 because the sample size. Okay, so that's where the dashes come in. Basically can't reject H0 because even if there's no overlap between the groups, it still doesn't tell us enough, because it doesn't give us compelling enough evidence at that significance level. So that's how the tables are made up. That's how we kind of do the calculations. But you'll notice that if we've got more than 10 in either of the groups, then we're not using these tables anyway, and we are doing this thing called this normal approximation. Okay, so at this stage I'm going to actually start doing the question, doing this particular question in this exam question, because this one does involve, what it doesn't involve, which is one of the reasons why I wanted to do that quick demo there, what it doesn't involve is actually making up the rankings themselves. Okay, so let's just do the question from start to finish. I'll try and not waffle on too much, but try and tell you the pertinent points about this test. It does want us to do a significance hypothesis test, so we need a H0 and we need a H1. So H0 is that the median of A is equal to the median of B. There's no difference. And H1 is that MA is less than MB, and that's simply because it's what it's asking for here. Sort of journey times, root A. Okay, so that's the hypothesis. This hypothesis, but we probably better define our variables, where MA and MB are the median journey times on route A and route B. Route B. Okay, so I'm often keen to use the word population when we're talking about our hypothesis. I don't think we have to here because of the type of question it is. A population is almost a virtual infinite population. So when we talk about the median here, we're talking about what the long run kind of median journey time, if we had enough time to do every single journey possible, which is almost infinite, and it's like almost sometimes called a virtual population. So I think we can get away without using the word population there. It certainly isn't in the mark scheme, so we don't need it. Right, so let's do the actual, let's get on with it. So we're doing the normal approximation. The normal approximation involves working out the mean and the variance. So for the normal, so RM approximately X normally distributed mean sigma squared, where that mean is equal to, let's look it up again, half m plus 1. That's equal to half times by, now the group sizes here, they tell us 17 and 12. Uh, 17 and 12, so, oh no, m is the smallest one, so that's 12. 12 plus 17 plus 1. That's equal to 30, 15 times 12, which is 180. And the variance, let's say this is given to you in the formula book, is that number there, 112 mn plus 1. Mn m plus n plus 1. So that's 112 times 12 times 17 times 12 plus 17 plus 1. Basically equals to 17 times 30, which is 510. Okay, so this is our approximate distribution, but note this is continuous. But this is discrete, and whenever we use a continuous to approximate discrete, we need to use a continuity correction. Let's just put a bit more kind of flesh on this before I get on with the question again. So again, just thinking of the kind of smallest that RM could be in this bit. In this situation, and the largest that RM could be. This is not something you'd have to do in the exam. I just think it's good to actually have this background information to help us understand what we're doing. Let's think of what the smallest possible RM would be. Well, that would be if all of the 12 are the smallest numbers, so it's 1 plus 2 plus 3 up to 12. Well, let's do our little regular formula for that. So it's 12 times 13 divided by 2, which is equal to 78. And the largest possible RM would be if they're actually going to start off, kind of the biggest that they could be. So that would be 29 plus 28 down to whatever that number is, but we can calculate that, and that's effectively what this is. So that would be equal to m times m plus 1, so it's 12. Oops, something's happened there. 12 times by 12 plus 17 plus 1. Okay, that's equal to minus is 78, and that comes to 282. And we've already worked out the median or the mean of this is 180, which is directly halfway between those. So the actual distribution of Rm starts off at 78, 79, so on, and then kind of peaks in the middle because it's symmetrical at 180, and then comes down here to the largest possible, which is 281 and 282, with all the numbers in between, of course. 181 and so on. So that's the actual distribution of Rm, and we're using a normal approximation. So I'll change colour here because this is actually what we're doing in the question. We're using the normal approximation, which has kind of asymptotes on it and the rest of it, with mean 180. Right. Okay, 180. And then we're working out this number here. This number here, and let's go to the actual question. The actual number we're dealing is 219. So 219, so 219 here, we're finding the probability, or approximating, well, all of these are added together, and if it comes to less than 10%, then we're rejecting H0. If it comes to less than 10%, all of these added together, but we're using the normal approximation to it. So when we do that, what we have to do is we have to actually kind of go, imagine you've got we need it to be less than or equal to 219. So we need Rm, let's write out the question here. We need Rm. The probability that Rm is greater than or equal to 219. That's what we're trying to work out, but that's approximately equal to this normal distribution. And what we have to do is put in this thing called a continuity correction, and we extend the number backwards by 0.5 or away from the number line. So that's 219. This would be 218.5. So that's approximately the same as the probability that this normal distribution, which is continuous, is greater than or equal to 218.5. And we can work that out on the calculator. So I'll just bring up the calculator now. So here we have it, menu 7, and we want normal CD. The lower number is the number we've got. We want the probability of it being greater than or equal to 218.5. The upper number, because we're dealing with the normal distribution, is some unlikely large number. Notice that in this actual distribution, 282 is the largest it could be anyway, but with the theoretical normal approximation, 500 would do, or anything larger than 300 or so. So let's put in our standard deviation, which is the square root of the variance, so that's square root of 510. And the mean is 180. So that equals to 0.441. 0.0441. So I often put continuity correction to make it clear what we're doing there. I'm just going to rub this out now because that's not actually part of our question. The diagram there might be useful, but this is not part of our question there. So that out. Okay, and neither is this to be as it comes, so I'll rub that out. as well. It's just kind of background information about what we're actually doing. Okay, so we can write that out. Let's move this up here. Probably nice to have the thing on the continuity correction on our diagram here. To have a diagram is no bad thing. So we've got, when we're dealing with the normal distribution, 218.5. So what's the conclusion? Well, it's 10% at one-tailed. So that's actually less than 10%. So we reject H0. So we're rejecting H0. And we can say there is sufficient evidence. We need uncertainty and we need context. So we don't want definitive, oh yes, it's, you know, there is sufficient evidence, sorry, there is sufficient evidence to suggest route A is quicker, has shorter journey times than route B. Journey times than route B. Okay, so that's that part of the question done. I would add as an aside, some of you might be saying, well, shouldn't I actually consider this question, this calculation? You can do it. It's not really necessary with the normal distribution, so long as we know which side of the actual distribution we're dealing with. But if you wanted to actually do it the other way, so the alternative, is to switch to left-hand tail. Which is what we have to do if we have larger numbers and we're using the tables. So switch to left-hand tail and do that calculation. So we have m plus n plus 1 minus Rm, and the Rm is the 219 we're given in the question. So that's 12 plus 17 plus 1. Take away the 219, which is equal to 141. So then you'd be dealing on the left-hand side of the tail. That's not very good normal distribution, is it? So then we'll be dealing with the left-hand side of the tail. 214, but we go back, we kind of extend the number back, and again, you'll find the numbers exactly the same from your calculator. If you put it in, you'll find the numbers exactly the same. So that would be an alternative. But I don't think it's necessary because you're doing one more calculation and you need to. In this case, it's obvious because the number we're dealing with, the ranking number we've got is actually 218 or 219, so 218.5 with the continuity correction for the normal distribution, which is more than 180. It's clear we're on the right-hand side of the tail, so we can do that. We can use that as our to work out our p number. But if you insist on converting to the left-hand tail, the smaller numbers you can do. It just involves that extra calculation. And as I say, if you're dealing with the actual using smaller numbers and using these values, you have to deal with the left-hand tail because we don't have the numbers, the critical values for the right-hand tail for that distribution. Okay, so there is one extra kind of 1 mark question to this, which I like to put in, extra question. State an assumption about the 29 journeys, which is necessary for the conclusion of the test to be valid. To me, the most obvious answer is that one of the assumptions is that the shape of the distributions not that they're just located in different places, but the shape of the distribution is the same, of distribution A is the same as distribution B. Okay, so that is a valid an assumption. You can also, the mark scheme does also highlight the fact that we're assuming that the sample is random, which we would do for many hypotheses, most of these hypothesis tests. But I think being more specific to this test is probably safer. So the shape of the distribution is the same of distribution A is the same as distribution B. So that's it. I hope you have found this in some way helpful. Goodbye.